Good evening, class. Today what we'll be talking about is using proportions to solve geometry problems. So we're going to look at the properties of proportions and how we can use them to solve things that we have troubles with. The first thing that we need to do is we need to have all those properties down. There's 4 of them. The cross product property is what we learned last time. I can take a proportion, multiply the means, and set it equal to the product of the extremes. The next 3 properties, each of these are something that will result in a true proportion. The only one that we really give a name to is the reciprocal property. And that's because it really doesn't change the proportion. But it does cause the ratios to be flipped upside down. So instead of it being 5 to 6, it might be 6 to 5. An example of what it would look like is off to the right on this PowerPoint. That's what the reciprocal property for proportions would look like. You take what you have and you flip it upside down. If you have A to B, it becomes B to A. If you have C to D, it becomes D to C. That's the only thing you change. Number 3, you can also interchange the means of the proportion. That means you can flip where the means are located and you will get another true proportion. And then the last one, I can take the denominator and add it to the numerator, and that is another true proportion. Let me use those 3 properties in an example. What if I gave you this proportion, and I asked for 3 other true proportions that you know, because you know this is true? Well, the first one, let's use the reciprocal property. Another true proportion I can make is 6 to 5 equals 12 to 10. All I did was flip everything upside down. Alright? Another true proportion I can make is if I change the means of my proportion. I flip them around. This number and this number are the means of my proportion. So I could make it 5 to 10 equals 6 to 12. That's another proportion I can make using that third property there. Well, the last proportion I can make is if I take my denominator here and add it to the numerator. So in this one, it becomes 6 plus 5 over 6 equals 10 plus 12 over 12. I take what I have in the denominator and I add it to the numerator. I simplify this as far as I can go. I get 11 to 6 equals 22 to 12, and yet again, I get another true proportion. So what these properties do, it allows me to change what I have to sometimes get into a more useful scenario. You might say, what might this be? Well, let's start looking at a few examples. The first example. All I'm asking you to do here is write 4 true proportions. Well, I also give you this information here that we already know this ratio to be true. Length of segment AB to length of segment BC is equal to the length of segment DE to length of segment EF. I actually think I messed up here. Nope, I didn't. I'm good to go. At this point, they want me to write 4 true proportions. That's other than the one they gave me. Well, the first true proportion I could write is, why don't I plug in the numbers? I don't want to have to deal with length of segment AB and length of segment BC. I'd rather deal with 5 and 6. So 5 is the length of segment AB. Length of segment BC is 6. Length of segment DE is 10. And length of segment EF is X. There I go. My first true proportion from the information given. Well, another thing I could do is the reciprocal property. What if I flip these upside down? 6 to 5 equals X to 10. Second true proportion. What if I switch the means here? Well, I'd have 5 to 10 equals 6 to X. Another true proportion. Well, last but not least, what if I add the denominator to the numerator? 6 plus 5 to 6 equals 10 plus X to X. There, I've written 4 true proportions, and those are the 4 properties. Taking the denominator, adding it to the numerator, makes a different true proportion. Flipping where the means are located, so in this case where 6 and 10 are located. Reciprocating it to both sides. And last but not least, just plug in the numbers you have. I've written 4 true proportions at this point. Let's apply it to a different scenario though. What if I give you a picture like this one? In the diagram, length of segment AB to length of segment BC is equal to the length of segment AE to length of segment ED. Find length of segment AB and length of segment AC. Well, let's look at what I have here. I'm going to take my proportion that I already have here, and I look at the numbers I have. AB I do not have. BC I have. AE I have. ED I have. Am I looking for length of segment AB? Yes, I could use this proportion plugging in all the other numbers to find AB. But what if my goal was to find length of segment AC? Well, that's actually the variable x. I don't want to use the variable y or z in this case. I just want to use x. What's a way that I could actually use the variable x here? Well, what if I took what I have here, and I took the denominator and added it to the numerator? Length of segment AB plus length of segment BC to the length of segment BC equals length of segment AE plus the length of segment ED to the length of segment ED. And I look, this part here is the combination of 2 segments, this one and this one, which I can call x. So instead of using a variable there, instead of using capital A and B, I can actually plug in the letter x. Awesome. BC didn't change from before. It's still 5. AE is 30. ED is 10. ED is still 10. Look, everything is now plugged into place. I didn't have to worry about accidentally calling length of segment AB x and then messing up my problem here. In this case, x actually does represent from A to C. Once I find it, I just set length of segment AC equal to it. Well, x to 5 equals 40 to 10. Cross multiply, I get 10x to be 800. And why did I say 800? I, of course, meant 200 there, for anyone that was paying attention. Divide both sides by 10, I get x to be 20. That's not my answer, though. I want length of segment AC. In this case, because x is length of segment AC, it's 20. If length of segment AC is 20, length of segment BC is 5, well, that means this last proportion right here has to be 15. So length of segment AB is 15. Done. We use proportions to solve for an unknown length. You're going to be using the cross product property, almost guaranteed, but you might be using these other properties so that way you don't accidentally misplace an x or misplace a variable and get something wrong. The next part that we need to talk about isn't just how to use proportion, it's actually talking about an application of them. There's this thing called scale drawings, and what we do is we make the shape. We just usually make the drawing smaller than the actual shape. With modern technology though, sometimes we actually make the drawing bigger than the shape, especially when we're talking about microchips. The drawing is way bigger than the actual chip for the computer will be. The dimensions of the drawing will have the same dimensions as the actual object. The ratio will be consistent. We make it to scale. And the scale that I'm talking about here is the ratio comparing the drawing to the object. In this case, in this picture, it says a scale of 1 to 100. Where's my mouse? It says a scale of 1 to 100. That means for every single inch on this drawing, there's 100 inches on the actual it's 100 times the size. So whatever the width is for bedroom number 2 or the kitchen, the width is 100 times bigger. Now, let's just say we took a scale drawing of a rocket. And I told you that in my scale drawing, the rocket has or is 4.5 centimeters long. And I said that the scale drawing to the actual rocket has a scale ratio of 1 to 10,000. What is the length of the shuttle? Well, let's compare them. All right. The only ratios I've been given have been drawing to actual, and that ratio was 1 to 10,000. So the actual object is 10,000 times bigger. Now, I told you that the length in my drawing is 4.5. So if I look at what I'm doing here, drawing to actual, drawing to actual. If I made another ratio here, I'm wondering what 4.5 centimeters translates to for the actual object. I don't know how long this actual object is, but if I'm looking for it, this ratio, the scale, has to be the same as what I actually physically see. If I see 4.5 centimeters, well then the actual will be 10,000 times bigger. 1 to 10,000. So that means these two ratios have to be equal. I set them equal. I have now made a proportion. The drawing will be proportional to the scale. The ratio of the object for any length in it will be proportional to the scale of the drawing. This here, by the way, the scale is the corresponding lengths in the drawing. So from actual to drawing or drawing to actual, that's a scale. Just be clear which way you're going. At this point, cross multiply. 1 times x is x. 10,000 times 4.5 is 45,000 centimeters. And there I go. That is the length of the shuttle, 45 centimeters. Done. Sorry, did I say 45 centimeters? 45,000 centimeters. Example 4. You buy a model, a 3D scale model. So it's pretty neat. It actually looks like the object. And the object that we have here, or the drawing or the scale model, is of the Reunion Tower in Dallas, Texas. The actual building is 560 feet tall, so kind of big. Your model that you built is 10 inches tall. And you know the diameter of the dome at the top is about 2 inches wide. What is the diameter of the dome, and how many times as tall as your model is the actual building? Well, if I think of what I have here, I can do the drawing or the model to the actual. I know that the height of the model is 10 inches. I know that the actual building is 560 feet tall. Wait, I also know that the model has a diameter, so the model, so that means I put it on top, has a diameter of 2.1 inches. And what they want me to find is the diameter of the actual dome. So I don't know what the actual dome is. So height of model to height of actual, diameter of model to diameter of actual. And I look, if this is a scale model, scale drawing, every single length in it is going to match up correspondingly, or proportionally, I should say. So in this case, 10 inches to 560 feet should have the same ratio as 2.1 inches to x. It's of the same model to the same actual building. So it should be proportional. I look at this. I don't have inches matching up to inches or feet matching up to feet. So what I'm going to do is use one of my properties. I'm going to switch the means about. So I'm going to switch 560 feet with 2.1 inches. 10 inches to 2.1 inches equals 560 feet to x. Because I have inches to inches above each other, the inches unit cancels out. My answer will be in feet. I don't have to worry about converting feet to inches or vice versa. All I have to do now is solve for x. 10 times x equals 2.1 times 560 feet. Well, 10x is 10x. And 2.1 times 560 is 1,176 feet. Oh, at this point, all I'm trying to do is solve for x here. Divide both sides by 10, I get 117.6 feet is the diameter of the dome. Awesome. However, they asked me another question. This wasn't the only part that they wanted. They also wanted to know about how many times as tall as your model is the actual building. So what they want to know is how many times it's taller, right? Well, 560 feet is the actual height. The height of my model is 10 inches. And the reason I'm going this way here is because I'm looking for how many times. If I do it this way, I'm going to actually get a whole number. Or at least a number that's larger than 1. And what that means is it'll actually tell me how many times larger the actual building is compared to my model. In this case, I will have to convert it to inches. So in 1 foot, there is 12 inches. So I'm going to take 560 and multiply by 12, and if done correctly, you should get 6,720 inches to 10 inches. Now that they're the same unit, the units cancel out. Divide top and bottom by 10, you get 672 to 1, so it's about 672 times taller. There I go. At this point, you should have a pretty good idea of how to use proportions. It's basically just doing the cross multiplying and setting up two ratios that you know are equal. There's this thing called a scale drawing that means the drawing to the actual object is proportional, or it has the same scale, it has the same ratio no matter what lengths I'm looking at. And there we go. Till next time.